hull computation. Okay, so I'll change the screen. I'll go to that screen share mode and use the whiteboard. Share screen. So everybody able to see that my screen? You're able to see that white screen? Yes, somebody has to respond.
Yes, sir, we are able to see.
Okay.
We are able to see.
So today what we will do, actually we'll take up the convex hull. Okay. So what is the convex hull? So anybody can say anything about the convex hull means? What does that means? Anybody can say what is a convex? See, we say that a object, yes, is convex. If you consider any 2 points, say x and y, which are belongs to this set, and if you take this line segment joining these 2 points, so this is the notation for the line segment. Line segment in the sense they're only line segment with x and y as the endpoints. So all the points inside this line segment also belongs to S. So well, I'm repeating once again. We call a set S. So we are calling a set S, okay, is convex if and only if for every points x and y belongs to this set, the line segment xy is belongs to S, then we call this S is a convex. This is a very general definition. We are not using this object is what type of object. Is it a closed object or open object, or is we are talking about 2 dimension, 3 dimension, 1 dimension? Nothing. A general definition. This is more very appropriate definition. Okay, for example, you take a one small this thing. You take any circle. This is a convex because if you take any 2 points inside and line joining these two, all the points on this line segment are within this one. Similarly, if you take ellipse, it is also true. It is true for every 2 points. Similarly, if you take a parabola, and if you take any 2 points on the boundary or inside, so all the points are belongs to this one. So in this case, this is a closed object and this is the open object. The parabola is open. So same thing, when you are talking about the circle in 2D, we can say same thing in the sphere in the 3D. Ellipse in 2D and ellipsoid in 3D. Parabola in 2D and paraboloid is in 3D. So all these things are convex sets, convex objects. Okay, so what is in which objects are not convex? So, for example, you take a polygon like this. Suppose if you take a point X and Y like this, and if you join them, okay, so this part of this line segment is not inside this object. Yes, so this is not a convex. So here the convex means all the points which are inside as well as on the boundary, everything together, actually what a solid object is what we call as a convex. So this is the actually mathematical definition of the convexity. So here I use the notation here. Okay, this is the line segment joining XY. Okay, and this one is a ray emanating from X and X is the origin of this ray and passing through Y. And in this case, this is the line segment. X and Y as an endpoints. And the third one is a line. Okay, this is line segment. Okay, and this is line. So if you take X and Y 2 points and line passing through them, okay, extended in both the direction. Infinite line basically. Okay, this is the line. And this is the ray, and this is the segment, line segment. So we use this notation in our book, in our discussion. So another thing is here, in this non-convex polygon, and this is what is called internal angles, no? So if internal angle is less than 180 degrees, less than pi, then we call it as a convex vertex. Okay, if it is greater than 180 degrees, then we call it as a reflexive vertex. Is that clear? So this is reflexive vertex, and this one is a convex vertex. Okay. So these are the definitions. Just whatever is required, whenever is required, just I'm giving definitions. Okay. Try to remember this thing. Okay. Now we have given one definition of the convex object or convex set. Now we will look at other possible definitions. Okay, there's first definition, second definition. Suppose X and Y are 2 points, or maybe I'll change it to X and Y instead of X and Y actually, P1 and P2. Okay, so you take some constant alpha 1, okay, some beta times of P2. Okay, with the condition that, okay, alpha plus beta equal to 1 and alpha and beta, both of them are greater than or equal to 0. And this is what is called a, okay, convex combination. Will come to that one. So if alpha is equal to beta is equal to half, then you will get a midpoint of these 2 points. Okay, so if you change the values by satisfying these 2 conditions, we will get, okay, all the points within this line segment. Okay. Now, is this clear? This is simple geometry actually, all of you know. And we extend this to a general uh, set of points, okay, what is called a convex combination. Of course, this itself is a convex combination, and this is can be extended to in general for any set of points. Suppose if P1, P2, P3, okay, and so on. Okay, suppose you have a PK points. Then alpha 1, P1 plus alpha 2, P2. Okay, with the condition that, okay, alpha is greater than or equal to 0 for all I, and sum of all the alpha i's equal to 1. Then we call this as a convex combination. This is a convex combination of these points. Okay. So if you see this one, the line segment P1, P2, okay, is a convex combination of its endpoints. The P1 and P2. So that's what we did earlier actually, this definition 2 here, okay. And similarly, if you take a triangle, okay, formed by 3 points, is convex combination of the points P1, P2, P3. See, in fact, if you take a triangle, so all the convex combination of P1, P2, what you will get is all the points which are inside this triangle. You can verify, okay? So this triangle is nothing but a triangle in the sense, not we are not talking about just boundary, okay? We are talking in terms of mathematical definition of the convexity. So boundary and all the points inside that solid triangle, okay, is nothing but a convex combination of these vertices. So for different convex combinations, you will get different points inside this triangle or on the triangle. Okay, so a triangle is a convex combination of its vertices. Similarly, if you go to this is a one-dimension case and this is two-dimension case. In the 3D, okay, you have a 4 points, okay. So P1, P2, P4, all the convex combinations of these 4 points is actually tetrahedron. Okay, it's a convex thing. So this is actually extended to any definition in any dimension. Okay. Okay. Now next thing is another definition. So suppose set of points are given to us. Okay. So assume that P1, P2, Pn, n points are given to us. So these points can be in one dimension or two dimension or three dimension. We are not talking about dimension, any points. Okay. For time being, visualize it as a two dimension, that becomes easier for us. So if you consider all possible convex combination of these points, okay. So that is what is called a convex cell of this set of points. Okay, is this clear? Convex hull of n points. Suppose, for example, we have a suppose n points are given a plane. Okay, large number of points are given to us. So what is the convex hull of these points? The convex hull of these points is actually, if you consider all possible convex combination of these points, whatever get all the points together actually convex hull of these points. Okay, intuitively it's not very clear how it looks like. Okay, now let's consider that these points are actually like a pins. Okay, inserted onto a board. Now you take a big rubber band, stretch it over these pins and release it. And whatever the shape this rubber band takes, that is what is the convex hull. Okay, so the rubber band takes a shape like this. So what is this? So if you assume that these points like a pins inserted onto a board, cardboard, and if you take a big rubber band and stretch it and put it over these pins and release it, whatever shape it takes, okay, this is the shape taken by this rubber band. This is what is called a convex hull of these points. So that is what the definition 3 is saying. So all the points which are inside are some convex combination of these points. So is this clear?
Yes, sir.
Okay. So here a slight variation of this definition. Okay. So what we'll do here, we are taking the convex combination of all endpoints. Instead of that, okay, if you take a only convex combination of d plus 1 or less, So here in D dimension. So when you think about 2 dimension, it is a D plus 1 is 3. Okay. So if you consider all convex combination of 3 points is convex cell of these points. Okay, just I write it down. So, for example, you take a 2-dimensional case. So let's take a less number of points. Okay. Now, convex cell of this point set is something like this. So what is saying? You take a D plus 1 or fewer points. Let's take D plus 1 point, the 3 points at a time. You take any 3 points. Okay. For example, I'll name them actually P1, P2. So let's take a points P4, P5, P6. Okay. All convex combination of these 3 points is nothing but this triangle. Okay. Now let's take another set of 3 points. Okay. Let's say now I'll take a P1, P3, and say P7. Okay. So all convex combination of these 3 points is nothing but all the points which are inside this triangle. So like that, if you start taking the three points at a time, and if you take the convex combination of all the points and you take the union of all of them, okay, what you will get all the points within this convex cell. Is this definition is clear? Any
Yes, sir.
questions here? So here we can take a fewer points also. What does it mean by fewer points? Suppose if you take a say 2 points, let's say P2 and P6. So all convex combination of these 2 points, nothing but all the points within this line segment. Okay. So basically you will get all the points within this one. That's all. So this is here in this definition we are using only D plus 1 points or lesser points in defined. That is the one definition, one difference between the previous definition and this definition. That's all. But still both of them you will get a same object, convex hull of these points. Okay. And another definition here is, yeah, we are trying to give a different definition so that we will get some properties of this convex hull so that we can use in the algorithmic sense, and so that we can compute it. We'll get a better understanding of this convex hull. Okay. Convex hull of this set of points S is nothing but a intersection of all convex hulls are a convex sets that contains X. So we have some set of points, yes. Okay, so let's consider this circle or an ellipse which enclosing all of them. Of course, this is not is neither a circle or ellipse. Okay, but this is a convex object, and which is enclosing all the points. Similarly, if you take a circle which encloses them, this is also another convex object which enclosing all of them. Okay. Similarly, you can take a some big triangle like this, which encloses all of them. So all these things are actually convex object which encloses the given set of points. Yes. Okay. Similarly, you can have a something like this also. Which also encloses all the points. So you take the intersection of all of them. So what you will get is a convex hull. So this convex hull also one convex set which encloses all of them. If you take intersection with this one with all of them, this is what will left. Okay, this is the another definition. Okay, now we will have another definition, a much more interesting one actually, which can be used to compute this convex hull. Okay, maybe we need before that we need some definitions. So we know actually two-dimensional plane. Okay, suppose if you take this one, this is a two-dimensional plane. Now in this plane, if you take a one line, infinite line, this line divides the plane into two halves. Okay, this is one half of this plane, and this is another half of the plane. Okay, so this is the off plane, what is called a off plane. Okay, so all the points which are one side of this line. Okay, so this is the one off plane, and similarly at this side, if you take this one, all the points which are this side of this line is a another off plane. So basically, what is happening here is this line divides the plane into two off planes. You understood what is off plane means? Or if you talk about in 3D, okay, you consider a plane. Okay, so you'll get an off space. So if you consider 3D, okay, three-dimensional space, you visualize your room. Okay, now you take a one plane. Okay, so that plane which is extended in all the direction divide this space in this your room into two halves. Okay, that is the one half space in one side of this plane, other half space the other side of the plane. In the two-dimensional case, okay, it is a line which divides this plane into two half planes. Okay, so off plane is, this is definition. Off plane means all the points which are one side of this line. So here actually we can also have a what is a open or closed off plane. When you say open means points on the line is not included in the off plane. The closed means points on the line also included in the off plane. They're just like an interval. When you say the interval is open or closed, both the extreme points included means it's a closed one. If the endpoints are not included, it's a open interval. In the same manner, so off plane is open means, okay, points on this line is not included. Closed means points on the line is included. Okay, this is the definition of the off plane. So how we can use this definition to define a convex hull? So convex hull of a set of points, yes, is nothing but a intersection of all the off plane which encloses this set of points. Intersection of, okay, all off planes that contain these points in S. Okay, so if you take these points, so this is one off plane which encloses all these points, and this is another off plane which encloses all of them, and this is another off plane which encloses this one. So like that, there are many infinite number of off planes are there which encloses these points. You take intersection of all of them, so what you will get a convex hull of this point set. So next definition is, so here convex hull of finite set of points is the smallest convex polygon, okay, which encloses all of them. If you see this, all the definitions earlier here, okay, the convex hull of these points is the smallest one intuitively, okay. So that we are putting it more formally. Okay, here the smallest means so there is no other polygon, okay, such that, okay, this P is a proper superset of P dash, and this set is a proper subset of, okay. If there's no such P dash is there, then we call this as a smallest convex polygon which encloses this. Yes. Okay, is it clear?
Yes, sir.
Yes, sir.
So another this thing is smallest area convex polygon, okay, that encloses this point set. smallest area convex polygon that includes this set is called a convex hull. Okay. So another definition is smallest perimeter. Convex polygon which encloses these points. Okay. These three points actually is looks okay intuitive, but it's difficult to prove it. Okay. The proof is little involved. So these are the things what we have about various definitions of the convex polygon. And you can have another this thing actually based on this whatever here this definition. Okay, so you consider all possible triangles and take their union. So that's another possibility. Okay, union of all the triangles determined by this points in S. So that also you can see very clearly, okay, from this figure. You take all the triangles which are formed by these points and take the union of all these triangles. That's what you will get a convex cell of these points. So you can, this is very clear from this definition, this figure. Okay, so these are the some of the definitions of the convex hull or convex polygon. Now, what we will do actually, we will give us some brute force algorithm for determining this convex polygon. So here one brute force method is finding the extreme points. Okay, extreme point is basically nothing but a point which are the vertices of the convex polygon of these point set. Okay, so how to identify these extreme points? Extreme points are nothing but here these points here P1, P2, P3, P7, P6. These are the extreme points here. Okay, so how to identify these extreme points? In other words, how to eliminate points which are inside or which are non-extreme points. So let's take an example here. So name them. So P7 is a non-extreme point. Of course, there can be any number of non-extreme points. Okay. So if you can eliminate all the non-extreme points, whatever left over is actually is a extreme points. So if you look at this previous definition, union of all the triangles determined by these points is the convex polygon of these points. So what we will do actually, if you take a non-extreme point here, this one, this will be part of some triangle. Okay. For example, if you take a P2, P3, P6, so P7 is inside this triangle. Okay. So you can eliminate P7 whether this P7 is included within the some triangle or not. So we use this observation. What we'll do, we consider all possible triangles and see if there's any point inside this triangles or not. If the triangle is inside, actually, then you can simply remove it. Okay, that is simple algorithm for finding the or removing the all the interior points or non-exterior points. So simple, you have a 3 nested loops. Okay, and we are considering this all possible triangles. So now consider this triangle. Okay, if basically if I is not equal to j is not equal to k. Okay, now you see this triangle formed by these 3 points contains any other point or not. Okay, so there will be another loop. Okay, maybe we'll put a one more this thing. Okay, before this, like this. And this point PL is inside. Okay, we'll write a notation, mathematical notation. So the point belongs to this one. Then, okay, PL is interior point. Or non-exterior point, you can remove it. So if you do this continuously, you will remove all the interior points. Whatever left over is the point which are on the boundary. Okay. So this is one simple algorithm to find out the points on the boundary of this convex hull. And obviously we have 4 nested loops. So n to the power of 4 is time complexity. It is too high. Okay. And the points which are there on the boundary, they are given an arbitrary order. Now we have to, okay, that is what the output we want, or we want to output the points on the boundary in the some order. Okay, so that is the second step. So if you want to points on the boundary in clockwise order, direction, anti-clockwise order, then you have to order them. So you need another step. So next algorithm is finding the extreme edges. So here extreme edges are, okay, so in the convex hull, so this is this edge, each edge is the extreme edge. Okay, so you identify these edges. Okay. So how we can identify? Now you consider a line passing through this particular edge. So all the points should be on one side. All the points are one side of this one. So that's what we have seen, one definition, all intersections of planes. Okay. So if you consider this one, 2 points at a time, and see all the points are one side or not, you check it. So if it is one side, then it's a extreme edge. So like that you do it. So basically what you have to do is for I is equal to 1 to n, and for j is equal to so basically we are checking whether I not equal to j not equal to k, and we are checking all the points are one side. Okay. So how we are checking? This pk, okay, is not left or on this PIPJ line segment. Okay, so all the points should be on the one side. You are considering left side. Okay, that means then PIPJ, okay, is not extreme. All the points should be on one side. If there's one point which side says other side, then this edge can't be a non-extreme. Like that, you can eliminate all the edges, okay, which are not extreme edges. Okay, so this way actually you can, another way you can find out the all the extreme edges, and this time complex stays order n cube. Of course, this is higher. So just two brute force method algorithms what we discussed to compute the convex cell are the points on the boundary or edges on the boundary of the convex cell. So in both the algorithms, we are not actually ordering the vertices or the edges so that we can output in particular order. That is not done. Okay. So suppose if you want to order them, then you have to execute once again. So that is the leaving it to the homework. Given a points on the boundary of the convex hull in arbitrary order, how you can order them so that all the points on the boundary are listed in the either clockwise direction or anti-clockwise direction. Similarly, for edges also, all the extreme edges of convex hull is given. How you order these edges in clockwise direction or anti-clockwise direction. So I'm leaving it to say your homework and try to solve it. And we'll meet tomorrow. So, and we decided to have a class tomorrow at 12 to 1. Okay. So before discussing about next class, so any questions till now, whatever we discussed today? Any doubts? Okay.
Sir, do we have to come up with the implementation or just the algorithm?
No, just use the algorithm. First you design algorithm, no need to implement. Okay. So you come back to the Teams. Okay. Stop presentation. Okay. So tomorrow we have a class 12 to 1. Is that okay? Anybody having a clash with any other class? Okay. I hope I assume that all of you checked this one. Still, if you have any clash, send a mail to me. So before I end, how many of you are there? Here, 9. How many? 18 only there? Anybody can count how many are attending?
Sir,
So that
59.
Huh?
58.
60.
How much? One of you, Mohit.
Yes, sir. 58 students.
58 students are there. Okay. Okay. Very good. So tomorrow we will meet at 12 to 1. Okay. See you tomorrow.